Today I'm going to talk to you. I was asked to talk about, the subject of thermodynamics and kinetics in organometallic reactions. And since this is the end of the week and it's been a lot of long days, what better than a lot of differential equations to end the week on? So we might see one or two of those, but what I thought I would do is to do this more like a workshop and show you how to use some programs as well as talk about kinetics and thermodynamics, and actually go through, how do you do a fit of a kinetic plot? How do you do a simulation? What do you look for? What are the problems that can arise when you do a simulation? Correlation of variables, we'll see problems like that. And then how do you adjust what you're doing to learn more about the mechanism and come up with a better way to extract information out of a particular reaction? So we're going to start off very simply with our first equation. Okay, hopefully nobody's shocked and falling out of their seat yet. Just talking about equilibrium. And so we all know what equilibrium is. We learned that as freshman chemistry. Products over reactants. And we heard in some of the talks this week, Joe, for example, had reactions that were only exothermic by a kcal or by 2 kcals. And you can see that when the driving force is small like that, the equilibrium constant is such that you're only going to 30 or 50 or 60% completion. So it's important just to have in your mind as a student what this scale is. That a factor of 10 is about a kcal and a half, and that even a million is less than 10 kcals per mole. Or if you want to learn what a kcal per mole is worth, it's about a factor of 5. 3, between 2 and 3 is about a factor of 100. And why is that an important number to know? Well, when we're measuring species in solution or determining how much is there, it's hard to detect, less than 1 part per 100. If we're looking at an NMR spectrum and there's 1% of something, we can barely see it. So that's kind of the region we work in, is a couple of kcals per mole in terms of equilibrium constant. And if we go beyond that, a couple of kcals per mole, we're just not going to see these species under a lot of conditions. So here's I've picked examples like Clark did out of my own research because I could just pull them up out of papers and out of my computers, not because they're the best examples, but just because they're there. So here's one. We had this nickel complex, nickel 0, binding to a nitrile. It undergoes an oxidative addition reaction. And what we found is this reversible equilibrium. The KEQ that we measure very easily by measuring the concentration of the product relative to the reactant was about 2. So that means this reaction is exothermic by about a half a kcal per mole. And we can draw a picture of free energy that looks like this. Reactants, some barrier to go over to get to the products. And that's the exothermic number that we get from our calculation. Remember, temperature is always in Kelvin. R can be in your favorite units, but I use 2 calories per mole. I'm a kilocalorie kind of guy. Likewise, we know that if you change the temperature of a reaction, you can affect the equilibrium constant. And the temperature dependence of K shows up in terms of the enthalpy, even though there's the temperature, T delta S, but it's delta H where this temperature effect shows up. You can get that by taking the equation delta G delta H minus T delta S and just rearranging it, and you see that log K, the temperature-dependent term, is delta H over R. It goes with delta H over R. The temperature-independent term is delta S over R. And this is the Van Hoff equation. And so again, if you look at the same equilibrium, what we found is that if you change the temperature in THF, it varies, and you get this kind of a dependence, a negative delta H, a negative delta S for the overall reaction. But if you go to a nonpolar solvent, it changes. Look, the slope is actually in the other direction. Delta H is positive and delta S is positive as well. And that occurs in this particular case as a result of this very polar nickel cyanide bond that you make in the product. So you can do these kind of studies and learn about the net change in bond energies, if you like, as you undergo this kind of a reaction. And then there can be these solvation effects as well. So I just wanted to show you how to use Excel to do some of this kind of stuff. So there's our equilibrium reaction, and what do we measure? At a given temperature, we measure an equilibrium constant. So most of you, I assume a lot of you have done this sort of thing, and we're starting out pretty simply. You just calculate 1 over t with that equation, the log of the equilibrium constant, and now you have the two variables that you want to plot in these two columns. And Excel has a nice feature. It's called trend. Has people done this with Excel before? So trend is just their example of fitting a line. And all you need to do is put in the range of the y values, the range of the x values, and then the x value for which you want to calculate it. So that's what I've got here, and here, and here, and here. The range of the y for the fit is always the same, and all we do is to change the x values, C4, C5, and so on. As we go down this row, column E, C is where it's reading the x variable. So that's how you get the calculated values in terms of a linear fit. And it's very straightforward to do. The next thing I wanted to show you is how you do statistics with Excel. And a lot of this is described in this book, Excel for Chemists. I don't know if anybody's used this before. But it's a nice resource to have in your laboratory because it'll tell you how to do a lot of these kinds of fits. Like I said, this is just a linear fit. It's pretty simple. All you have to do is you select a 2x5 block for the array. And there it is. You have to type all this in. Linest is there Excel's keyword for doing a statistical analysis. And in the 2x5, if you just hit Shift, Control, Enter with that formula up there written in, then you'll produce this block of this array. It's a 2x5 array. You can't delete it because you can't delete an element of array. You can only delete the whole array. And that shows up because it's in these brackets up top. Whoops, they're gone now. See? Can't change part of an array. All right. So you put that in. What this gives you then is the slope and the intercept. And then it gives you the standard error of the slope and the standard error of the intercept. And it's those errors that we want to get out. The standard error is just the standard deviation divided by the square root of the number of observations. So it does that for you. Once we know the errors, that's really what we're interested in because we want to get over here the enthalpy and the entropy. Well, there's the enthalpy. It is delta H over R, negative. So we multiply by R to get back our delta H value. I divide by 1,000 to get kcals per mole. And then I've got plus or minus some number. And a lot of times what we quote, sometimes we quote the standard error. And you should state that in a paper, what your errors are, if you're quoting standard error, so we quote standard error. Or a lot of times we like to quote 95% confidence limits, which means that we have confidence that 95% of our measurements would fall within this range. And the way you get that with Excel is right here. It's this T inverse and then 0.05, meaning 95%. And in this case, there are 2 degrees of freedom. We have 4 data points, but 2 of them are used. 2 degrees of freedoms are used, one for the slope, one for the intercept. And so that's why right here we have only 2 degrees of freedom. And so you type that in there as well. And then again, I'm scaling it to give us calories, to give us kilocalories per mole. And then I put this round-off function in there just so we get 2 significant figures. So that's how you can do that. There's the entropy part. It's just the next entry, G5. It's this error instead of F5 for the error. So you can set up tables like this, and once you set up a spreadsheet like this, every time you do a Van Hoff plot, you just pull it up and modify it, and you don't have to type this all in again. All right? So that's how you do that sort of thing. So again, this is just the slope plus or minus t, the student t-test, times sigma, the standard error, and likewise the b times the t-test, and then the standard error. So here's the other plot for the THF example. It's got a lot more data. We've got now 6 degrees of freedom. Our errors are going to be a little bit better because the value of t that we multiply will drop down. So that's how you do a line fit and how you get the error out. Excel also has another way to do it. Let's see. Tools, data analysis. And what we do is we go over here and load in regression. And it'll ask you, the Y input range, so you can select the Y input range and the X input range. You select that, and then you tell it where you want to put the output and say OK, and it will print out this information over here, which is the same thing that we did on the left, only it's automatic. So it'll give you your intercept, your slope, your standard errors, your 95% confidence limits, all automatically. So you can use that function if you want instead of doing it manually as we did over here. Okay, so that's the first example I wanted to show you, is just one of these simple line fits, in this case to the Van Hoff plot. There's the student t distribution. So most of you have tables like this. Again, for a number of degrees of freedom and for 95% confidence limits, you can look up the value of t that you'll multiply the standard error by to get your 95% confidence limits. A lot of people don't treat error very well when they quote a number that they measure, a rate constant. You should always quote the error and the source, the way you calculated the errors. And in the literature, I just find it's not done all that rigorously. So we're still on the subject of equilibrium and thermodynamics. What about an equilibrium where two particles go to make one? Because now if you write your equilibrium constant with concentrations, you're left with units. And how do you handle units? So let's talk about equilibrium where there's two particles going to one. And how do you handle the problem of units? Because right away, if you have concentration over concentration times concentration, K has units of reciprocal molar. Yet, as we know, how do you take the log of a number that has units? You can't. So in fact, the way equilibrium constant is defined, go back to your junior P-Chem course, is every concentration is really relative to the concentration in a defined standard state. And we choose for convenience in solution a standard state of 1 molar, and then the units, if you like, cancel. So now K is a unitless number. Yet we always express units with K, so we'll remember what our standard state was. But K is unitless, but it does depend on your choice of standard state. So they do not have units, but they refer to a standard state. There are different numbers of reactants and products, then choice of the standard state will matter. If there's the same number of reactants and products, then if you like, they will have the same units in the numerator and the denominator, and it's not usually a problem. So typically we choose for liquids, for solutions, 1 molar, for gases, 1 atmosphere, or for neat material, we'll choose the neat material. And again, we have to remember what our standard state is. So let me show you where that comes into play. First of all, here's a molecule undergoing substitution by 1 isocyanide and then 2 isocyanides. And the equilibrium constants, if you take product over reactant, is uphill. It's less than 1. And then this one's uphill again. So we can produce a free energy picture that looks like this. For that number, it's uphill by 1.2. For that number, it's uphill by 1.9. But since we have 3 particles going to 3 particles going to 3 particles, the standard state won't matter. Whether at 1 molar or a tenth molar or a millimolar won't matter. Okay, we'll get the same result. But and we can just measure this by NMR. It's very straightforward to do. But now, let's look at a situation where you have some, say, metal complex dissociating a ligand. And let's suppose in this example, the equilibrium constant is 0.25. It's less than 1, so the reaction's uphill thermodynamically, right? Delta G is such that it's uphill. So if we have 1 molar of this material, we'll have 0.5 and 0.5 of that to give us our KEQ of 0.25. The reaction's uphill. Fine. But now let's look at a different position of equilibrium. Suppose we're working with a more dilute solution. This is only 0.04. Then at equilibrium, these will be 0.1 each. Wait a minute, now there's more product than reactant, yet delta G is positive. See how that's where the confusion comes in. And it has to do with the fact that the equilibrium constant here, if you like, has units. It's referred to the molarity, 1 molar, as the standard state. So this picture, if you like, refers to our standard state equilibrium, not to the position of equilibrium in a given set of circumstances that we're using. So if we do have concentrations that are different from standard state, and we have different numbers of reactants and products, there's a correction term, RT log concentration, relative to the standard state concentration. And so I just showed that pictorially here. If we're at half molar products, then there's a correction term, RT log a half molar over 1 molar. So that's really the case we have for the first one. And then for the second one, where it's 0.1 molar here, that correction term is so large that it actually is downhill. So this is no longer the standard free energy, it's the free energy under the concentration conditions we're talking about. So when you have unequal number of particles, these free energy pictures, you have to be a little careful. Because if you just take the numbers you get out of your fits, those are standard state numbers, and they may not apply to the exact situation. So here's an example that we ran into. We made this phenyl hydride compound, and when you heat it up, it eliminates benzene and cyclometalates. And it goes to completion in hexane. But if you do it in benzene solvent, it goes to 97% completion and stops. Because the benzene that's so concentrated is able to compete and go back. So you measure the concentrations of each of these, you get an equilibrium constant of 397 using 1 molar as the standard state. This was the concentration we were working with. So you can write down Km. It's 0.0316 molar that. That's our starting concentration. It's 97% that. 11.2 is the molarity of benzene. And divide by the concentration of the reactant, 2.7% of that. And that's how we get our equilibrium constant. But this is already a pain in the neck, because now you got to know the molarity of your material, not just the ratios of these things. And a better way, or a more common way to treat these kind of equilibrium problems, we have unequal number of particles, is to use the mole fraction. Work with a mole fraction equilibrium constant. Because now this is just the 97.3% product. The mole fraction of benzene, if it's the solvent, is 1, or nearly 1. And the mole fraction of this material, 2.7%. So the mole fraction equilibrium constant is unitless, and it's easy to work with. Not only that, we now know, what if we just went to a solution that was 10% benzene and hexane? What do? Well, it's easy. That's 10% benzene is a mole fraction of 0.1, which is a correction to the free energy of RT ln 0.1. So corrections with mole fractions are very easy to do compared to molarity. All right. So a lot of times it's better to use mole fraction to denote your standard state. Let's talk a little bit about rates and show how they're related to equilibrium. So here's a delta G, a reaction, and there's a forward reaction and a reverse reaction. And the rate in each direction can be expressed using the Eyring equation. So this is the rate constant, Boltzmann's constant, divided by Avogadro's number times Planck constant times the temperature, e to the minus delta G over RT. Hopefully everybody knows that equation, or you've seen it already. So you can calculate for a given rate constant what the delta G is, what this barrier height is. And the way this works is you can sum the delta G of the forward and the delta G of reverse, and that adds up to be the delta G for the reaction. So if this delta G is large, you can measure this rate, but it's hard to measure the back rate, because when you go back, you go forward all the way. So it's hard to measure delta G directly by measuring these two if delta G is large. Let's talk a little bit about the Eyring equation and the barriers that you encounter. So here I've shown some typical half-lives from a microsecond to a month. That pretty much covers everything we're going to run into in the lab for most of us. So rate constants of 10 to the 5th to 10 to the minus 7th. At room temperature, here's a benchmark. 40 degrees, 10 kcals per mole. Barrier means it lasts a microsecond. Okay, so if you have a reaction with 10 kcal per mole barrier, a microsecond. It's gone pretty fast. Here's another benchmark. Room temperature, a minute is 20 kcals per mole. That's a fast reaction, right? One that goes in a minute. So that's 20. Remember that number. Here's one over here I picked out, 30 kcals per mole. That's 100 degrees a day. So maybe a reaction that you're going to reflux overnight, 30 kcal per mole barrier. So most of the time in the lab, we're dealing with barriers between 20 and 30 kcals per mole for most reactions we do. So just kind of remember those numbers as well. 25 is a typical barrier for a reaction we would do on the benchtop. All right? And then you can see as a function of temperature, these vary a little bit. Here's a first-order reaction, starting simply, just a simple rate constant. We know that the concentration is a function of time, e to the minus kt times the initial concentration. The product grows in, according to this function, it's the inverse of the exponential, and then shifted up by that amount. So we can plot log concentration versus time, and we should see a smooth exponential for this reaction. So the way we would normally do this is to have time, concentration, take the log. Okay, so we just create a column with the log of the C over C naught, or A over A naught. And we get these numbers. So that should be a linear relationship between these two. So once again, we'll use our trend function and calculate the values. So that's shown on the plot on the right. The squares are the data points, and then the line is the calculated value. So you can plot that data up like that. You can use the line est once again. Here's your array that you set up. to fit that data, and it will calculate a slope, an intercept, and then the two standard errors. So that's one way to plot the data. The other way to plot the data with Excel is shown down here, and that is just to plot the log function itself. Don't bother to plot a line. Just fit the log itself. So we have time, concentration, and now we can calculate a log function. And the way Excel does that is with this thing up here called growth. Wonderful. So they call a log function a growth function. And where is it? There it is. So growth, you put the range of y values, the range of x values, and then the x value where you want to calculate. And it will calculate then the logarithmic function shown here. And that's what this line is. So you can fit the log decay itself just fine. I also show here the growth of B, and it's just the initial concentration minus the amount of A. So that's the growth of that material as well. These are exactly the same thing. And again, we can fit statistics to the log decay. And so instead of line est, they use log est for the function. But it will give you exactly the same information with regard to the value and with regard to the error. So hopefully most of you have done this kind of thing with Excel. And I just wanted to review all this just so we're all starting on the same page. So here's another example. And what I did was to take that fake data that I just showed you and go ahead and change it a little bit such that the decay is not to 0, but above 0. Okay, so I offset the data. But now we're just going to go ahead as if we're thinking it's decaying to 0 and plot what happens. And as you can see, we get a pretty good straight line. Here's the concentration. It starts at 0.7. It goes down to 0.36. All right, that's only about a half-life. But look, we get a nice linear fit. Well, it's pretty linear. Here's the log, that same function, showing how that's the ultimate concentration that I fit it to, that it actually is going to go to. So this is a decay to that final value, yet we're fitting it as if it's going all the way to 0, and we get a nice fit over one half-life. What you can see is if you look at the error as a function of time, it's not random error. It's below 0, it's above 0, it's below 0. So in other words, that's a bowed fit. Okay, we're not fitting it very well. You can see that better if we go not one half-life, but if we go out to 3 half-lives. So I just took that same data and let it continue on, and you can see we're starting to level off out here at about whatever that value is, 1.2. And now the line fit isn't very good. So this is a lesson about doing a first-order fit. If you're going to do a first-order fit, if you're going to fit kinetics, you should do it over 3 half-lives minimum. Because over 1 half-life, as you saw, lots of things look linear. So you need to fit the data over a substantial portion of the reaction. All right? Otherwise, you'll run into those other problems. So let's do that. How do you do that kind of fit? Because now we're a little more sophisticated. Here's our data going down to our final value. Time, concentration data over 3 half-lives. There it is down there. Okay. Calculated value. We have C0 minus C infinity. C0, C infinity. We don't know what that value is, but we can make a guess from our plot. And then we have e to the minus k t. And then it's offset by this amount. That's the infinity value, C infinity. So how do you do this kind of fit? And already Excel is stumped because it doesn't have a built-in function to do an exponential decay to a non-zero value. So I thought I would show you how to do this sort of a fit. And we're going to use a program or a built-in feature called the solver. All right? So all we did here is calculate the value with that formula. And these variables, C0, Ci, and K, are in this table over here. C0, C infinity, and K. And let's mess with them. Let's make this one 0.75. All right? And see our 0 isn't as good. And we can sit here and play with these for a while. 0.17. And try and get a good fit of our data when we don't know what these values are. 0.014. All right, we're not doing too well. But you can sit there and play with those 3 variables for a long time to try to optimize the fit. And Excel does have a way to do that. What you can do is you vary these 3 numbers. And it will do that for you. All we are going to do is to calculate the error, which is calculated minus observed, right there. And then take the square of that number. And then we're going to sum all of those squares down here. So that's the sum of the squares. And what we want to do is to minimize that quantity to do at least squares. So the solver will do that. Tools, add-ins, and there it is, the solver. It's not in by default, but it's part of Excel. And so now we've loaded that module, and we go Tools, Solver, and here's what comes up, this little box. So let's take a look at this. It says set the target cell, and the target cell is going to be that square of the sum of the errors. We want to minimize that. Whoops. Let's keep it right there, E32. And we want that to be to a minimum value of 0. We want to minimize it to 0. And we're going to do that by changing these cells. Those three right there. Okay? And all we do is say, solve. Boom. Okay? And it adjusted those three values to give us the best least squares fit. Here's a plot of the error as a function of time, and you'll see it's randomized. Okay? How do you get the error? How do you get the statistics on this sort of thing? Because that's usually the next thing we're interested in, right? So there's another thing you can load. And this doesn't come with Excel, but it comes with this book. It's called Solver Statistics. So it runs a macro, and now it's in a hidden window. So it's a program that will calculate all this stuff for you. Okay? So you can get it here. It'll be on the website or wherever you get all these files. So you can get the solver statistics. Okay, so now that's been loaded. Let's go back to log versus time. Tools. Solver statistics now appears. And it asks you things. The range of known y's. So that's our concentration as a function of time. We select those. We say OK. Range of calculated y's. They're right here. Say OK. Least squares coefficients. Those are these three, right? OK. And then it wants a matrix to put our data in. We'll do a 3 by 3 and say OK. So it now gives us our value. That's the same as that. But now it gives the standard error with it. So for each one of these, we now get the standard error. There's our rate constant and the standard error. So that's how you can do errors with the solver. How many people have done that before? A couple of people. So Excel will do these things. But as you can see, you require add-ons and that. It's not very good for the scientific stuff, I don't think. What else? Oh, I have one other thing here. We use the solver, but this time we fit the growth. And I won't go through this, but I just want to show you that this value, A0, 0.59. No, it's not. It's 0.79. A infinity, 0.1. No, it's not. It's 0.2. So what's going on? And when you fit the growth, all we can get is the difference between these 2 points. We don't know how far offset this was originally. So these two will track each other. They might be 0.7 and 0.2 or 0.8 and 0.3. The difference is what it will fit, but it can't get them independently because when we fit the growth, we don't know what the infinity value is for the starting material. So that's just kind of an interesting. You can play around with that. I don't want to take time to do that today. Well, we made it to first order so far. How are we doing? Let's go ahead and, we just talked about all these. First order decay to non-zero. That was this example. It looks linear over 1 half-life, but when you go to 3 half-lives, there's trouble. You can fit this with the solver, and you can get the statistics using solver statistics. You can also fit the growth, but there's this correlation that shows up. All right, here's a real example. Approach to equilibrium by HD exchange of a methyl deuteride, K forward, K reverse to make this material. You can see this material goes away. This one grows in, and you kind of get to equilibrium near the end. And the observed rate constant here of approach to equilibrium is the sum of the forward and the reverse rate constants. The equilibrium constant is the ratio of the forward and the reverse rate constants. So we can fit this with a solver, use solver statistics, okay, and you can pull out the values as shown here. So I've done that as well. Maybe in the interest of time, I won't go through that example, but that's on there if you'd like to go and take a look at that one as well. Okay. Temperature dependence of rate. We talked about the temperature dependence of KEQ. What about rate? And again, we have the Eyring equation that has that temperature dependence, but notice that it appears linearly here and exponentially here, so it's complicated. So if we rearrange this equation, replacing delta G of activation with delta H minus T delta S, we get ln K over T versus 1 over T will be linear in minus delta H over R. And then the intercept is delta S over R minus the log of these parameters. So minus 23.76 in kcals per mole. So when you do the temperature dependence of a rate, you get a plot, log K versus 1 over T. And from the slope and the intercept, you pull out delta H and delta S of activation. Another way to get rate constants that's well documented in the literature is to do NMR techniques such as complete band shape analysis. So the example I picked is this molecule, cyclopentadienyl rhodium. This is a phenyl group and a bromide, but there's hindered rotation around the metal phosphine bond. So in this toluol group, the paratoluol, there are 3 different methyls. And so you see that here it is just below room temperature, 3 different methyls. And as you raise the temperature, what you observe experimentally is these 2 coalesce first, and then all 3 coalesce, and you get a peak at the average of those 3 locations. So that's the observation. How do you get the rate, the barrier for that? You can download software. There are a number of programs that will do this for you, where you specify the 3 chemical shifts, and then you specify the rate constant for the interconversion, and it will calculate a spectrum for you. And all you do is to do a matchup of observed versus calculated. And here, with that rate constant, we get a good match. With that rate constant, and so on. And you can literally just do this by eye, adjusting the rate constant to get a good match. And you'll come up with temperature versus rate constant data. And that's what you need for an Eyring plot, and there it is. And you can see that you get a good line all the way down here to 0. Very good statistics in terms of the error, because this is over a wide temperature range. The other method we've used is to use kinetic measurements to determine thermodynamics. We've studied a number of reactions where this exothermicity is so great that you can't measure the equilibrium constant directly. You can't get a direct measurement. And this is just an alkyl hydride or an aryl hydride or some kind of hydrocarbon reacting with another hydrocarbon to undergo an exchange. And that spread has been so big that we could not measure them directly. So we resorted to an indirect way to measure that, and that is to measure this barrier, which is the barrier for loss of one hydrocarbon, to measure this barrier for loss of that hydrocarbon, and then do a competition where you generate this fragment in a mixture of the 2 hydrocarbons and get this difference in selectivity. And now you have 3 delta Gs, and you can sum those up and come up with this number down here. So here's an example. We use this tris-perazole borate rhodium compound that when you shine light on it loses this ligand. Very clean, quantum yield of 1, very easy reaction, 15 minutes, it's done. You shine light in benzene, you make the phenyl hydride. If you heat the phenyl hydride up in deuterobenzene, benzene comes off, deuterobenzene goes on, and you measure the rate. It's very slow, half-life of months, but you can measure that rate. Get the barrier. You can do this experiment, irradiate in T-butylethylene. Do vanillic activation. This eliminates, without making a without making an olefin complex, it falls off completely in benzene. You make the free olefin in this, and you measure that barrier from that rate. Eyring equation. Then you do a third experiment. You do a competition, benzene versus the alkene. 10-to-1 ratio corresponds to this kinetic selectivity. And so now you can add those numbers up, the kinetic selectivity, the 2 different rates, and get the delta G naught. So this is a general method. Wolzansky used this, I believe, in his titanium amides to undergo hydrocarbon exchange and got a huge range of delta Gs with that particular system. In our case, here is a summary of what we did. Kinetic selectivity for a wide range of hydrocarbons is pretty small. From the best to the worst is only a factor of 22 to 1. The best, the fastest substrate versus the slowest substrate. But in terms of thermodynamics, 11.5 kcals per mole, that's 220 million to 1. You'd never measure that directly. So a big difference here for these, but a small difference kinetic selectivity. So you can get that sort of information, that kind of detailed information, just by doing simple first-order kinetics and competitive selectivities. All right. To save you a lot of anguish, I thought we would do some examples of some simulations today. One is a kinetic simulator. One is a least squares fit of the simulations that you do. And it's available at this guy's website. And they developed this program, 30 years ago for enzyme kinetics. And it's still available. It still works well. It was updated about in the year 2000, the last time. It was originally written in Fortran. So this version has been compiled and made to run on a PC in a DOS window, but it's still a Fortran-based program. I believe there is a Windows version that you can now buy for Mac and PC if you want to buy a copy, and then it's a little more user-friendly. But if you just go to that website, you can find it. And it's Carl Frieden is the faculty member there who came up with this, as I said, a number of years ago. All right. And there's help files and all that sort of thing. So let's start with a simple one. A goes to B. So this is just our reaction we've been talking, a barrier to a product. But remember, every reaction is reversible. It's just a matter of how reversible it is, how exothermic it is. So we're always going to treat reactions as if they are going in both directions. So we'll use that A and B data from that plot that I showed you before. Let's just try fitting that with a simulation now instead. And there are several steps to use these programs. First of all, you have to prepare data files. You have to run the KinSim and enter initial concentration, rate, constant times. Your best guess as to what those are. And you have to do this Fortran compiling business, which means clicking on some buttons. And then you run in the FitSim to do the fit itself. And then you look at the output. So that's the general procedure to do a simulation. So here's how it works. Here are the programs, KinSim and FitSim. And they run in DOS, and DOS needs this little DOS program. That's all standard stuff that comes with, your computer. Here's what you have to type in. First of all, $sign is a comment. Remember, this is Fortran, so it's going to be a series of lines. And there's our mechanism. A equals B. Equals means two arrows going in each direction. That's all you have to type in. No differential equations. Nothing. Star output, and then the data that you want the program to output. I want it to output the concentration of A, and I want it to output the concentration of B. Couldn't be easier, right? No differential equations, no rate equations, no nothing. Just the mechanism. And you'll see how powerful that is in a minute. Let's run, I've got data, text files, time, concentration. That's A going away. It's just the data we saw before in the text file. B going away. All right, and we'll run this KinSim. And it's DOS. That means it won't crash and it's really fast. But it's all keyboard driven. Let's see. So let's start with our mechanism. The first thing we need to do is Command O, compile the mechanism, because it's Fortran. So O. Input file name, what was it called? AB? AB.mech? Right? Oh, good. It likes it. And we're going to put it out as AB. And it's called AB.something else. All right? So now we'll load the mechanism. Up top, Command M. And it's called AB. And we can do view the mechanism. So now the program understands this. A goes to B. There's a K plus one, and there's a K minus one. And it's going to output those two. Okay? So now we need to do some concentration work. And I've already forgotten what the concentrations were. They were in this file, weren't they? 0.7. Oh, and it goes for 350 minutes. All right, so we'll go back to DOS. All right, change concentrations. So we'll put in 0.7 for the initial concentration of A. Concentration of B is 0. And we'll do escape. I think it's Control E to escape. There. And then we'll put in our rate constants. Gee, I have no idea. I forget. 0.02 or something like that? And we'll say there's no reverse reaction for now. All right, and what's next? Rate constant, output factors, time factors. We have to put in the increment of time that we want it to calculate. Let's have it do it every minute. We'll leave all this at the runtime was what, 350 minutes, I think? Yeah. Y max was 0.7. So you put in that sort of stuff. And these other things, you know, you can play with all these variables if you have more complicated systems. So we've done mechanism, time. Okay, and I think we're ready to go. I'm going to save this, call it AB. So I just saved all those numbers we typed in. And then we just do G for go. Oh, and there it is. So that's our simulation. It's saying it goes away like that, and it comes in like that. So how do you compare that to the real data? Well, again, this is a Fortran program, right? So the first thing we need to do is somewhere, A, convert ASCII to RDF data. It wants to read all this stuff in. I told you it wasn't easy. Somewhere, 3, we have 2 files. One's called a.txt, and we'll put it out as a.rdf. The other one was called b.txt, b.rdf. And the data are in 2 columns, right? All right. I don't care about any of this stuff. So now we can include the real data in our plot. There are 2 files. A.rdf, there it is, it found it. B.rdf, it found that too. And then we do go. So now, there's our real data, and there's our fit. Not too good. What's wrong? Let's see, our rate constant's too fast, right? So we can go back to K, change that to, I don't know, 0.015. That's slower. Exit, go. All right, it's getting better. All right, and you can play with this for a while if you want. But the other thing we can do, we've saved all this information, is quit, is we can go to the other program called FitSim and have FitSim adjust those values for us. All right? And remember, it's not going to 0, is it? Now, I only put in K1. I forgot about K2, K minus 1, right? Well, FitSim can adjust that if we want. We know that K1 and K minus 1 will balance to equal the equilibrium constant, which was some finite value. So let's just try it and see what happens. FitSim, and it has fewer choices. So 1, make the files up, and it's going to ask a new mechanism, yes. It's called ab.simulation, and we'll take defaults for a lot of this stuff. Okay. Equilibrium constant, or constant variation. K1 we want to vary, so we put in a code of -1. K minus 1 we want to vary, we do -1. The options are vary it, fix it, or link it. So you can have 2 rate constants linked together as a group. Group 1, Group 2, Group 3. That's very powerful because a lot of times rate constants are linked to each other, and you can vary them as a group here. And those are the only 3 options, varied, fixed, or linked. So we'll get out of there. That's a good guess, somewhere between 0 and 10 to the 10th. How many data sets are we fitting? 2. And it wants the save file. We called it ab.save when we saved it. RDF was a.rdf, and that was our first output variable. Name of save, ab.save, b.rdf, 2. 1 all default, sure. And that's it. We've set up the files to run the fit, and then 2 will do the fitting. All right, that's our file, and boom, it's done. So it's very fast. 2 degrees of freedom, sums of squares. There are rate constants, the values, and the errors. Oh, look, it fit K1 and K minus 1. Notice that the standard errors are about 1%, so it's a pretty good fit overall. I think it was 0.999 for the correlation. We'll get out of there. Press the key, and now 3 will show us those fits. Oh, 1. Is that what it says? I can't read that. Enter to view all at once. All right, what happened? Try it again. Fits in. I hit the wrong key or something. We want to view the fits is 3. Huh. Oh. Do we have the... Let me see if the file's there. Yeah, here it is. Here's our log file. Here's our input file. Let's just take a look at the output log. So here's A to B. There's our equilibrium. Here's the data set that it read in. Here are the rate constants that we put in. There's all these parameters. These are the cycles of regression. And it seems to have crashed right there. All right. Let's run it one more time. Fits in. 2. I must have hit the wrong key. So it's all done. 3. There we go. I must have just hit a wrong key. So now you can see the data, and you can see the fit, and it's excellent overall. So this is a nice program because it's more complicated to run, as you can see, but it does a better job of giving you your fit. You saw how easy it was to enter the mechanism. No typing in formulas or anything like that. Oh, and there's the comparison from Excel versus FitSim. The results are identical within the error limits, okay? They better be. Here's another one. Look at this mechanism. This is getting pretty hairy. I gave you a handout, or I assigned a handout from Atwood's book where they go through this example. And the first case they do is irreversible, K1, K2. So just A to B to C, all right? And you can write down explicit equations for all these rates. Likewise, for the reversible case, you can write it down, but it's a lot more complicated. All right, there we go. A to B, reversible. So here's forward and reverse rate constants. We'll assume the second one is irreversible. You got to solve this secular equation for the roots, so you need the quadratic formula. This is in Atwood's book, how to do all these things. You have observed concentrations for 3 species. A goes away, B goes in, comes in, goes away. Here's C coming in. And then you have the calculated values. Oh, and look at that equation for the concentration. It's horrendous. And for A. All right? And that's just for this simple case. Well, you can use solver. You can fit these. To save time, I'm going to skip that. Okay? But you just come in and do solver, and you've got your observed, and all that sort of thing. And you can fit it. And that's what these solid lines are. Those are using these numbers up here. Okay? That's what we have over here. So Excel will do that. The problem is Excel won't give you the statistics anymore because now we have 3 sets of data, not 2 that we're fitting. So it won't give you very good... You can get statistics on one number or the other number, but not both at the same time. So I've found that as soon as you get to a situation like this, you are better... And there's the equations. Oh, my goodness. And they get even worse as you go to... that was reversible with the fit. Here's the irreversible case right there. So it gets pretty hairy. So what I've found is method 2. Go to KinSim and FitSim. No equations are needed. All right? Instead of typing all that stuff in. So let's try that. Here's KinSim, FitSim, A, B, C. All right. So the way this works is I have the data. Here's A. All right? It's going away. Here's B. It's growing in. Then it goes away. And then C grows in. And we have the same through. We need to make a mechanism file. Oh, and that's a sample. I put all the answers up here. And I'll just get ABC mechanism, copy, paste. Let's take a look at it. So that's what you type in. Comment, A to B to C. The rate equations. You don't type rate equations, you type the mechanism. A goes to B, goes to C with equal signs. And we want to output A, B, and C. So it's very simple to set up. And the hard part is to run the DOS stuff. Okay, KinSim. Here it is again. We've got to go through this. First, we'll compile the mechanism abc.mech, abc, and it'll call it .sim. We'll load it, abc. We'll view it, and there it is. Okay, K1, K2, K minus 1, K minus 2. We'll enter concentrations. Oh, geez, I forget what they were. Mine like a sieve. Yeah, let's take a look. 0.1 this time, not 0.7. So we'll do the concentration. So A is 0.1. That's it. Rate constants. I have no idea what these are. So we'll just put in 0.1 for the forward reaction and 0.2 for the second one. I don't know. We'll see how it looks. You got to guess those. The time factors. 1. And how long did this run for? I don't know. 250 minutes or something? Ymax was 0.1. Okay. We need to get our data, so we convert data. 3 files. A.txt, A.rdf. B.txt, B.rdf. C.txt, C.rdf. 3. Too many choices. We'll include that data. 3 files. A.rdf. That's it. B.rdf. C.rdf. And I think we're ready to go. Go. Oh, all right. There's our data. Here's our calculated values. Look, they're way down there. Way too fast. All right, way too fast. All right, so let's change those. Instead of 0.1, 0.01, and 0.02. Control E, go. Oh, there you go. They're getting close. So you can sit around here and mess around with this for a while if you want. I'm just going to save it. ABC. So it's saved as ABC. We can pull that up without typing all that in again. So we've got all these files now, the Fortran data files. We'll just go to FitSim, show you how this works quickly. Make files for fitting. abc.sim. Okay, we'll take all defaults. What do we want to vary? Let's vary everything. Except K2, we know it goes to completion, so we know that the final step is irreversible. And we'll leave all those at default. Number of sets, 3 data sets. abc.save. A.rdf was the first one. abc.save. B.rdf was the second one. abc.save. C.rdf was the third one. All defaults, sure. Fit. That's our input file, and it's done. So it's very fast, as I said. There are 3 rate constants, and there are the errors. It's not bad. Control exit. And now let's take a look at the fit. And there's the fit. So again, you can see the data and the fit, and it all works out pretty well. You can export those numbers into Excel, and you're off and running. So I found this to be a useful program because it's so easy to, no rate equations, no differential equations. You just type in the mechanism. This is an example, A to B to C to D. All right? And when you look at the data, here's A going away. This chloro derivative goes away. It's converted to a hydride that grows in and goes away. It's converted to the N-propyl hydride that grows in and goes away. And you can see that this stuff is growing in slower than the final product. So there must be another way to get to the final product. So we include that pathway. Well, that's easy to do with KinSim, FitSim. 4 data files, right? Because there are 4 species that we get from our NMR integration. Here's our mechanism. A to B to C to D, and then we added in a pathway B to D. And then the 4 output variables. That's all you have to type in. Then you enter your initial concentrations. I'll just go to the fit. And let's see, what do we want to look at? Let's run KinSim. So we'll just run this KinSim. So all we have to do is load the mechanism. IPRH. There's view it. So there's what it comes up with. The 4 steps that we just talked about. Since all the parameters in there, I'll just restore them. IPRH. And go. So there's what our initial guesses are for the rate constants. And I don't have the data there. We'll just go ahead and run FitSim. And I've got the file already set up. So all we do is run FitSim and start fitting the data. And there it is. So it's already fitted. And there are the values that it comes up with. 0.24 with an error of 0.005, 0.04 with an error of 0.001, and so on all the way through. So very fast, very easy to do. And view the fits. There you go. So more complicated, very easy to set it up and run it. Yeah, this is just another example of something going away and something growing in and something else go away. The reason I wanted to show you this one is we have a methyl hydride. It's the same one as before, the methyl deuteride, scrambling. But competitive with that, slowly the methane falls off. All right? So we've got a disappearance, a growth, and a disappearance. And then this one is just the growth of the product. So there's not much data here. You've got basically an exponential decay, and then an exponential growth and a decay. So kind of 3 observable things. Yet there are, in this mechanism, 5 rate constants. An elimination to make a methane complex that rearranges. It's readdition. It's addition to CH. It's elimination, and then the dissociation. You don't have enough information to get 5 rate constants out of this fit. Well, what happens if you try to fit it anyway? All right? And so I wanted to go through this example for just this reason. We don't have enough data to do this. TP rhodium methyl deuteride. Okay. And you got your data files, as I said, a.text, c.text. We got a mechanism file. Where's our mechanism? Here it is, methyl deuteride mech. Let's look at this one. So A to B, that's our sigma complex of methane. And then A prime is our scrambled material. And then B can fall off to make C. That's all you have to put in. We want to look at A prime, and C. We don't want to look at B because it's never there. It's the sigma methane complex. There's not much of that around. It'll always be near 0. So that's our scramble. That's our situation. We can run KinSim. We can run FitSim. And let's just look at the output, the log. So here's our mechanism. K1, K-1, K2, K-2. That's the scrambling. And there's the dissociation. It's irreversible, so we know K-3 is 0, so we don't vary that one. We left that one and fit all 5 of the other ones. What happens? There's our 3 sets of data. All right, there's the one we're going to fix at 0, and we're going to vary these 5. There are no groups. Blah, blah. It goes through and fits it. Has some trouble and fits and does some more. It's a smart program. Here's the output data. This time we added output it. And here's the result. All right. Here are the 5 rate constants. And here are the errors. The first one, K plus 1, 1.2 times 10 to the minus 2, an error of 10 to the minus 4. Pretty good. Second one, 3 times 10 to the 7th, an error of 4 times 10 to the 8th. That's not good. The next one, K plus 2, 3 times 10 to the 8th, error of 5 times 10 to the 9th. That's not good. The next one, 10 to the minus 2, error 10 to the minus 3. Thumbs up. And the last one, 10 to the 7th, error of 10 to the 8th. Is this meaningful at all? And sometimes you do simulations, you get results like this, and you have to scratch your head and think about it for a week. So let's take a look at what's going on. At the output, at the very bottom, it lists what's called a correlation matrix. We have 5 variables. And it will show you how these variables correlate with each other. Each variable 1 correlates with variable 1 exactly. So the correlation coefficient is 1. So all along the diagonal, you have 1s. Variable 1 and variable 2 correlate with a negative 0.54. That means if one goes up by 1, the other one goes down by 0.54. But look at this one, 0.9997. It's pretty darn close to 1. This variable, variable 2, and variable 3 are correlated. If one goes up, the other one goes up exactly the same much. They're tracking each other. Variable 2 correlates also down here with variable 5. And likewise, you can see right here, variable 3 correlates with variable 5. Well, what the heck are those variables? So there are the 5 variables that we varied. And the red ones are the ones that are in trouble because their errors are way too big. And those are also the ones that are correlated with each other by unity. So what happens is those 3 variables are moving together. They're tracking each other. We can't determine those rate constants. Whatever they are, whatever one of them is, the other 2 track with it. Okay? We can't learn those rate constants from this experiment. But we can get the other ones, and their errors are fine. What does it mean physically? Well, here's our free energy picture, right? We started here, we went here, and then eventually we dissociated. We don't know the energy of this species. We never saw it. So we don't know where this species is. That means we can't determine K minus 1 because we don't know the energy of this. So if this goes down in energy, this barrier becomes larger. But this barrier, K2, and this barrier, K3, become larger by exactly the same amount in terms of delta G double dagger. So those 3 variables are correlated with each other. We don't know what they are, but they will track one another exactly. We can get K1, we can get K minus 2 just fine. So that's what we learned from this simulation. We learned the absolute rates, K1 and K minus 2, and the relative rates of K minus 1, K2, and K3, but not the absolute rates. Now, we just typed in a mechanism, so the program automatically figures out the differential equations. Okay? So they are there, but they correlate one with the other. All right? And one way to get around this is to assume a value for that oxidative addition based upon some laser flash work that Bergman did. They did some flash experiments with TP, rhodium carbonyl, and measured the rate at which oxidative addition occurs from an intermediate. So if we just assume that's the value for one of these steps, that pins the other 2 to that value. And then we can do our simulation again and get out, fixed rate constants, if you like. But they're all tied to the one that we put in, the one that we can't get from the deuterium scrambling experiment. All right? So I wanted to choose this example, like I said, because it's a simulation that kind of goes wrong, but it's not meaningless data. In fact, if you think about what you're measuring, there's no way you can get these very fast rate constants because we don't know the energy of that sigma complex that's involved in the intermediate. But the rate constants are correlated. Right? Oh, this is just that same simulation. And now see if you fix this one, then you can vary these other 3 and get very good parameters on all of them now. And you learn about methane dissociation versus oxidative addition. So this is stuff we published, a couple years back. And then all those files are dumped in the SI, right, of the FITs. But now you know how to do it, okay? Jed did the same thing with Jed Parkin with bis-CP tungsten methyl deuteride. Used the same program, same everything, and did the same kind of stuff. And that's just a summary. Oh, just to show you the power of this. We were wondering about propane and our metal. When the metal reacts with propane, all we see is the top right, the N-propyl hydride. We never see secondary activation. So how do you know where the metal binds? Does it bind in the middle, or does it bind on the end? And how can you tell? Because if it binds to the middle, it could migrate to the end and insert. All right? So what we did is a number of experiments, like the one I showed you, the isopropyl chloride converted to the isopropyl hydride, converting to the N-propyl hydride, but we did it with deuterium instead. So we could learn about these relative rates of measurement doing simulations. And I'm skipping all that, okay? Because I wanted to focus on this problem. How can you tell where it binds? And the way we figured out to do that was to do a competition. And we did this competition, decane versus pentane. Because those 2 hydrocarbons, if they're in 1-to-1 mole ratio, there's as many methyl groups on pentane as there are in decane. But decane has 8 methylenes. Pentane only has 3. So if binding to the methylene is important, you're going to get more decane activation. And that's what we see. We get a little bit more decane activation. And see, the problem is the metal might bind to the middle of the decane, but it doesn't just walk to the end and insert. It's a random walk. It can go back and forth as it's walking, and then there's always a chance to fall off. So it's not as efficient as you might think to have all those methylenes in the middle. But how can you quantify that rather than just have this loosey-goosey kind of feeling about how this works? And the answer is with KinSim and FitSim. Well, with KinSim, and I like to show this slide because there are 20 different compounds. They are all the different alkane complexes of pentane. The methyl, the next methylene, the next one, and the methyl. But you can only activate at the end or the other end. So there's 7 species. And I don't know how many rate constants. It looks like 12 rate constants. But a lot of these are the same rate constant. They're just for migration from methylene to methylene to methylene to methylene. Or from methylene to methyl, that's a different one. Or from methyl to methylene. And then there's an insertion rate constant. And once you're here, you can dissociate from a primary or a secondary. But we assume that the secondary and the secondary are all the same. And you can coordinate to a methyl or a methylene, but we assume that that's the only 2 variables for coordination, a methyl group or a methylene. Then you do the same thing for decane, and there's just a whole lot more compounds. But once you set this up, there are 64 rate constants. It's getting pretty complicated. But there aren't 64 different rate constants. There's only about 6. And what we do is we do a simulation. Here's our mechanism. That's it. Couldn't be easier, right? Pentane, 5 species plus the 2 CH activation adducts. Decane, 10 complexes plus the 2 CH activations. And each one, the metal A, the fragment, can coordinate to any position along the interior of the chain. So that's all you type in. That's the whole mechanism. That's that big slide that I had before. That's easier to type in than draw on that slide. And then the output, we want to see everything, all these complexes. So you do that. And all we did was to run a simulation in this case, and it's called DP. DP. View it. Oh, there it is. Look at all those rate constants, right? The hardest thing is just to keep track of all of it. Let's restore DP and go. And there it is. It's kind of, you can't see too well, but all these alkane complexes are down here, and they go away. And here are 2 compounds growing in. One is decane, the other is pentane. And so all we do is adjust the 2 coordination rate constants to a methyl or a methylene to match what we see in the experiment. This is pure simulation. This is a manual fit. So we just adjust binding to methyl versus methylene to get the right rate. And when it's 1.5 to 1 binding rate ratio, we get the right answer. Okay? Another interesting thing is early on in the simulation, look, you get as much decane as pentane activation. Why? Because each one has 2 methyl groups. When you bind to the methyl, you activate. Okay? So that shows 1-to-1 ratio. And it's only later on that you get differentiation. That's because the decane has all these methylenes and the metals migrating up and down and eventually gets to the end. So the simulation of this was actually pretty trivial, considering how complicated the system was. So that's how you do simulations. This was an interesting, a real mechanism problem that we did. Platinum thiophene activation. What happens is if you take this compound and add 2-cyanothiophene and heat it up about 150 degrees, this comes off and this goes on. And initially you get mostly this stuff with the cyano group away from the metal. But if you wait, I don't know, a month or something, it goes over to this stuff, 48 to 1, 49 to 1, something like that. So kinetic product, thermodynamic product. And what we found is that the reaction's bimolecular. So you add more of this, and the rate increases. Here's the concentration that we add. Double it, double it. The rate constant doesn't quite double. It's not quite linear. As a matter of fact, I've drawn a curve to lead your eye. What does that mean? It's a bimolecular reaction, but it's not linear. Well, what we discovered is that if you plot 1 over the observed rate constant versus 1 over the concentration, now it is linear. So what does that mean? And if you are paying attention during Clark's talk, it's a Lineweaver-Burke type plot. And what it means is we have a pre-equilibrium followed by a rate-determining step. Okay? So when you think you're looking at a bimolecular reaction, and the rate seems to be tailing off, not doubling for each doubling of concentration, try the double reciprocal plot. And it's very common in organometallics. Something has to happen first, and then something happens. All right? So that's what we did, and we do this plot from the, this is the equivalent of the kinetics that we saw earlier. Here's an easy way to write down that expression by inspection. Here's the mechanism. So the rate of disappearance of this material is K1 times the concentration of that material, compound 1. All right? Now, once you get here, it has a choice. Go on or go back. Let's look at that fraction of how much goes on versus how much goes back. The amount that goes on is K23 out of the amount that goes back is K minus 1. The rate that goes on is K23 times the concentration of this stuff. The rate that goes back is K minus 1. So the fraction can be expressed right there. It's called the success fraction. So we make the intermediate at this rate, and then the success fraction that goes on there, that's the rate expression. No differential equations, no nothing. You just write it down. And that's just some observed rate constant, because if this stuff is present in excess, it doesn't change much. And so we just have a first-order reaction. But K-obs, is all this stuff, is equal to this. And if you just plot the reciprocal, that's the double reciprocal plot. 1 over K-obs, 1 over concentration of substrate is a straight line. The intercept is 1 over K1 right there. So we get K1. We get this rate constant from this plot. And then you get K1 relative to K minus 1 and K23. Well, we know K1, so we get K minus 1 relative to K23. We get the amount that goes on versus the amount that goes back from the slope, from this slope. And there it is. K1 is that number. K minus 1, the rate at which you go back versus goes on, is that number. So in other words, at 0.346 molar, it's 50-50. Okay? So that's what we get from this analysis. Well, we go there and then we substitute. But I said over time we go here. So here's the actual distribution of species. Starting material goes away. We make initially the one isomer, but then it goes away and the other stuff grows in. All right? So how do we treat that kind of a system? All we were looking at was the disappearance of starting material. How do we include that? Well, KinSim, FitSim, once again, will do this for you. There it is. So it fits this very nicely. All right? No problem. 5. What's the mechanism file look like? Here it is. That's what we have to type in to get KinSim. A to B are intermediate. B goes to C. B goes to D. And then C and D equilibrate. So that's all you have to type in. Then you put in your data. Do the KinSim. Do the FitSim. Just as we just did. And you get all that information out. So from KinSim, FitSim, we get the actual values for these different rate constants like that. All right, I'll finish up with this example. It's just kind of curious. We made these, as I said, methyl hydrides, methyl deuterides, a bunch of different combinations. Here's the methyl deuteride, CD3D, in benzene. You get a rate for its elimination. And that's this one, blue. All right? Then you do the methyl, the proteo, in benzene. And you get this one. And that's this one in red. But then you do it in deuterobenzene, and you get a different rate, just a little bit different. Why should there be a solvent isotope effect on the rate of methane loss? Because this thing should lose methane, and then the benzene should be activated. How can there be a solvent isotope effect? So we varied the concentration of the solvent. What we did is to take our benzene and dilute it in perfluorobenzene, which isn't activated, and look at the rate of the reaction as a function of the benzene concentration, or I should say mole fraction. And you can see that as it goes more and more dilute in benzene, the rate slows down. And so if you plot that, you see that the K-obs versus the concentration isn't quite linear. And I've drawn a curve to guide your eye to head towards that asymptote. So once again, we have a bimolecular reaction. It looks like, but it's not quite linear. This must be a pre-equilibrium followed by a rate-determining step. You do the double reciprocal plot as shown over there, and it's a nice straight line. So we've almost proven the mechanism. What happens? Methyl hydride eliminates to make a methane complex first, and that's a reversible equilibrium. then there must be a bimolecular step where the benzene replaces the methane before it's activated. We don't see any of these. All we did was that simple experiment changing proteo to deuterobenzene and then change the concentration of benzene. And it led us to come up with this whole mechanistic hypothesis. All right. And that's just the summary. So that's where we began in terms of the abstract I sent out. I've tried to give you an appreciation for kinetics in a way you can use it in the lab, that you guys can. I mean, we've all done first-order plots. We've all done equilibrium constants. So let's take it to the next level. Let's do our error analysis properly. How do you do these more complicated cases? And they weren't that complicated. They're nothing like we saw earlier. This is just, one or two reaction steps. Maybe a reversible step, maybe a bimolecular step. And right away, you get to the point where you can't do integrated rate expressions. They're too complicated. So simulation takes over. At least for me, it's a lot easier. And what I wanted to show you is that simple program. It's a little pain in the neck to run, but it's an oldie but a goodie. And it's a very smart program in terms of the way it handles rate constants that are 10 to the 8th and 10 to the minus 8th in the same expression. Because if your rate constant is 10 to the 8th and you put in a step size of 1, let's see, that's 10 to the 8th molar, then it's going to change it in one step. Well, that just physically doesn't make sense. But the program knows how to handle all that stuff because it's an oldie but goodie. So simulation is very useful, and you can use it in the studies you guys are doing in the lab.